Welcome to Tell Me More Stories Told Us podcast.
Great to be here.
Today we're setting off on a bit of an adventure. We're diving into a world that's all around us, but often totally unseen.
That's right. We're talking about industrial piping.
Exactly. And forget, the leaky faucet under your sink for a
Yeah,
minute.
we're going much bigger scale here.
We are talking about vast networks of tubes, the real arteries of industry moving everything from, raw materials to essential gases, sometimes across huge distances.
It's a fascinating hidden world, really. It underpins so much of modern life, but people rarely think about it.
So today we're going to unpack what this piping thing really is. Our sources give us a great look at the engineering, the materials, even some surprising history.
Yeah, the history part is quite something. You wouldn't expect it.
Our mission then is to explore this hidden network. You might be surprised, it's a lot more than just tubes carrying stuff.
Definitely more.
Okay, so let's start right there. When we talk about piping in this big industrial sense, what exactly are we referring to?
Well, fundamentally, it's a system. A whole system of pipes designed to convey fluids, that means liquids and gases, from point A to point B within an industrial setting.
An engineered system then, not just pipes thrown together.
Oh, absolutely engineered. The whole discipline of piping design is focused squarely on moving these fluids efficiently and, crucially, safely.
Okay, so it's not just the metal tube itself. What else is part of the system?
Right. It's much more. You've got all the inline components. Think fittings, which are the pieces that connect pipe sections, change direction, that sort of thing.
Like elbows and T-junctions.
Exactly those. And then you have valves. Valves are critical for controlling things, the flow rate, the pressure, even the temperature of the fluid inside.
So you can turn things on, off, adjust how much is flowing.
Precisely. It's a very controlled environment.
Hmm.
And all of this, the pipes, the fittings, the valves, the instruments, it's all meticulously documented
How so?
on drawings called piping and instrumentation diagrams, P&IDs for short. They're like the definitive roadmap for the entire system, incredibly detailed.
Complex roadmaps. I like that analogy. And I heard sometimes the word piping itself refers more specifically to the layout, the actual design work.
Yeah, that's true too, especially when talking about the detailed design within a plant or facility. Nowadays, that's almost always done using sophisticated CAD software.
Computer-aided design, so they build it virtually first.
Exactly. Allows engineers to see everything in 3D, optimize the routes, check for clashes, basically iron out problems before any actual pipe gets installed. Saves a lot of headaches down the line.
Makes sense. Now, most of us know about plumbing, right? The pipes in our houses, businesses. How does that relate to this industrial scale piping? Is it just a bigger version?
Well, yes and no.
Hmm.
Plumbing, which handles, drinking water, maybe natural gas for heating. Wastewater removal, that is technically a type of piping system. Fire sprinkler systems are another example you might see in buildings.
Okay.
But industrial piping is often on a completely different level. Think about scale, first of all. Huge refineries, massive chemical plants, power generation facilities.
Right, the sheer size.
Yeah, and also the substances being moved. We're talking raw materials, semi-processed chemicals, high-pressure steam, volatile gases, things that demand much more robust engineering and materials. The pressures and temperatures can be extreme.
Okay, so definitely not just connecting a few hoses then. It's serious engineering. What's at the core of that engineering discipline?
It really boils down to three main areas, or subfields, you could say. First, understanding the piping material itself, what it's made of and how it behaves.
Makes sense. Material choice must be key.
Absolutely fundamental. Second is the piping design, the layout, the routing, the components we talked about. And third, and this is a big one, is stress analysis.
Stress analysis. That sounds intense and important.
It is utterly critical. Pipe stress engineers are basically the structural guardians of the piping system.
Guardians? How so?
Their job is to meticulously check everything. The proposed routes for the pipes, the forces acting where pipes connect to equipment, those are called nozzle loads. The placement and type of pipe supports, hangers, everything.
And the goal is
To make absolutely sure the pipes can handle all the different forces or loads acting on them without bending too much. Or worse, breaking, without exceeding the material's stress limits. Failure is obviously not an option in these environments.
right. You mentioned nozzle loads. Can you give an example like where a small pipe joins a big tank?
Exactly like that. Or where a pipe connects to a pump or a large vessel. That connection point, the nozzle, has to withstand the weight of the attached pipe. Any thermal expansion or contraction, vibration, all sorts of forces. Calculating those loads accurately is vital.
Okay, so what kinds of forces are these pipes dealing with day in, day out?
Well, there's quite a range. You have what are called sustained loads. That's basically the constant stuff, the weight of the pipe itself, plus the weight of the fluid inside it and the internal pressure.
The baseline stuff.
Right. Then you have operating loads. These are related to the normal running conditions, the pressure and temperature fluctuations during operation. And they even have to design for pressure testing loads. Before a system goes live, it's often tested at a pressure higher than its normal operating pressure just to be absolutely sure it's sound. That test itself puts stress on the system.
Wow, okay. That covers a lot. But I guess there are less predictable forces too, things that don't happen every day.
Oh, definitely. Engineers also have to account for occasional loads. Think about things like earthquakes or high winds, especially for outdoor piping runs.
Right, environmental factors.
Vibrations, too, maybe from nearby heavy machinery. And then there's something called water hammer.
Water hammer, you mentioned that. What is it exactly? Sounds dramatic.
It can be. It happens when a fluid flowing quickly through a pipe is suddenly stopped, like if a valve slams shut. The momentum of the fluid creates a pressure wave, a shock wave, that slams back through the pipe. It can cause significant damage if the system isn't designed for it.
Yikes. So how on earth do engineers figure out if a pipe design can handle all of that? Earthquakes, water hammer, constant pressure.
They don't do it with pen and paper anymore, generally. They use specialized computer software. Programs like AutoPipe, Caesar2, KypeIP, there are several major ones.
And these programs.
They allow engineers to build a really detailed 3D model of the piping system. Then they can input all the different load conditions, pressure, temperature, weight, seismic data, whatever, and the software simulates how the pipes will respond. It calculates the stresses, the strains, the movements.
So it predicts potential problems before they happen.
That's the idea. It's all based on complex engineering mechanics principles like finite element analysis in many cases.
Okay. What about really extreme conditions, like, say, moving super cold liquids? Cryogenics.
Ah, yeah, that brings its own challenges.
Yeah.
When you get down to very low temperatures, like with liquefied natural gas or liquid nitrogen, some materials, particularly certain steels, can become brittle.
Brittle, like they could just snap.
Potentially, yes. They lose their ductility. So engineers have to be incredibly careful with material selection for cryogenic service. They need to analyze the temperature gradients along the pipe and choose materials that stay tough even when they're freezing cold.
Fascinating. And I suppose even tiny flaws in the metal could be a weak spot under all this stress.
Absolutely. Stress tends to concentrate at sharp corners in the geometry, or, yes, at internal material defects, maybe tiny inclusions or microscopic cracks from manufacturing.
So quality control is paramount.
Hugely important, from the steel mill right through to the final installation.
So when they're doing these calculations, these simulations, are they basically treating the pipes like big, complex beams, supported here and there?
That's a pretty good way to think about it, at least conceptually. In the stress analysis software, the pipe is often modeled as a series of 3D beam elements. The software knows the material properties, the dimensions, and where it's supported or anchored. Then it calculates all the bending moments, shear forces, axial forces, all the stresses.
Gotcha. And you mentioned specific pipe grades for tough industries like oil and gas, approved by ASME.
Yes, ASME, the American Society of Mechanical Engineers, publishes widely used codes. And within those codes, there are specifications for particular grades of pipe suitable for different services. For oil and gas, you'll see various carbon steels and alloy steels designed specifically for things like high pressure, high temperature, or corrosive environments.
Okay, let's pivot slightly to the materials themselves. You said material choice is fundamental. We've talked a lot about steel, but it's not just steel, is it? I saw a surprisingly long list of possibilities.
Oh, far from just steel. While carbon steel and stainless steel are definitely workhorses, used in vast quantities, the range of materials used for piping is incredibly diverse. It really depends on what fluid you're moving, its temperature, its pressure, its corrosivity.
So give us some examples that might raise an eyebrow, things beyond steel and basic plastic.
Okay, well, you mentioned plastics. We see things like HDPE, high-density polyethylene, quite a bit, especially for water or gas distribution. But how about non-ferrous metals, like cupronickel?
Cupronickel, copper and nickel.
Yeah, it's an alloy. Fantastic resistance to corrosion, especially from salt water. So you see it a lot in shipbuilding and offshore platforms.
Ah, makes sense. Anything more exotic?
Well, for handling really, really aggressive chemicals, sometimes you need something incredibly resistant. You might even find pipes lined with tantalum.
Tantalum, isn't that quite a rare, expensive metal?
It is. But sometimes its corrosion resistance is just unmatched for a specific nasty chemical, so the cost is justified.
Wow, okay. What about nonmetals, besides the plastics we might recognize, like PVC?
Sure, you could actually have pipes made of tempered glass.
Glass pipes, seriously, wouldn't they just shatter?
Tempered glass is pretty tough. And the advantage is transparency. In some chemical processes, being able to visually inspect the flow is really important. So yes, glass piping exists.
Huh, never would have guessed.
Yeah.
Any others?
Teflon-lined pipes are another one. Teflon, or PTFE, is famously inert. It resists attack from almost anything. So you line a standard steel pipe with Teflon for handling highly corrosive fluids.
It really seems like there's a material solution for almost any challenge. It's amazing.
The material science aspect is huge, yeah. Always trying to find the right balance of strength, corrosion resistance, temperature tolerance, and of course cost.
Now, this might sound really basic, but thinking about all these advanced materials, what did they use way, way back, before steel was common, before fancy alloys?
The history lessons. Actually, one of my favorite parts. Believe it or not, some of the earliest pipes were made out of wood.
Wood. You mean like drilling a hole through a log?
Pretty much exactly that initially, just boring a hole down the center of a log.
That is incredible. I can't even picture that working well.
Well, later on, they got more sophisticated. They developed something called stave construction. Think about how a wooden barrel is made, with individual shaped pieces, the staves, held together with hoops.
Okay, like barrel making.
Same principle. This made the pipes easier to transport in sections and assemble on site. And wooden pipes were actually super useful in, say, mountainous areas. Imagine trying to haul heavy cast iron pipes up a steep slope back then. Wood was much lighter.
Resourceful. But still, wood, wouldn't it rot or leak?
You'd think so, wouldn't you? But wood actually had some surprising advantages, especially compared to early metal pipes.
Like what?
For one, wood doesn't expand and contract nearly as much with temperature changes as metal does. That meant fewer problems with leaks at the joints and less need for complicated expansion loops or joints in the pipeline.
Interesting. Less movement.
Also, the thickness of the wood provided some natural insulation. It helped prevent water inside from freezing in cold weather, which could be a big issue with metal pipes.
Okay, that makes sense. Insulation.
And here's the kicker. Wood, when it's constantly saturated with water, doesn't actually rot very easily. Plus, it's immune to electrolysis.
Electrolysis, what's that?
It's an electrochemical process that can cause metal pipes, especially different metals connected together or buried in certain soils, to corrode quite rapidly. Basically, stray electrical currents can eat away at the metal. Wood, being non-conductive, doesn't have that problem at all.
Wow. I am genuinely learning things here. Wood pipes had actual advantages, so they were pretty common.
Oh yeah, quite widespread for a long time, especially for water transport. And here's a specific fun fact for you. In the western United States, redwood was a really popular choice for making these wooden pipes.
Redwood. From those massive trees, why redwood?
Redwood has amazing natural properties. It's inherently resistant to weathering, decay, acids, even insects and fungus. It's just naturally durable.
So redwood pipes would last a long time.
They did. And another interesting thing, the inside surface of a redwood pipe tended to stay smooth over time. Early iron pipes, on the other hand, would often corrode and get rough inside, which restricted flow and could lead to clogs. The redwood stayed smooth, maintaining carrying capacity.
That is absolutely fascinating. Redwood pipes. Smoothing the flow. What a great piece of history. Okay, so let's fast forward back to the modern era. With all this complexity, these different materials, the high pressures, there must be rules, right? Strict rules and standards.
Oh, absolutely. You can't just design and build these critical systems based on guesswork. The entire industry operates under a framework of very specific standard codes and specifications.
But a rule book for piping.
Exactly. These codes ensure safety, reliability, interoperability of components, and consistency across different projects and industries. They cover everything from material specifications to design calculations, fabrication methods, inspection, and testing.
So who makes these rules? Who are the big standard-setting bodies?
There are several key organizations whose standards are used globally. Probably the most well-known in North America is ASME, the American Society of Mechanical Engineers.
ASME, right. You mentioned them regarding pipe grades.
Yes, their B31 code series is fundamental. There are different sections for different types of piping. B31.1 for power piping, B31.3 for process piping, B31.4 for pipelines, B31.8 for gas transmission. It's very comprehensive.
Okay, so ASME is huge. Who else?
Another major one is ASTM International, formerly the American Society for Testing and Materials. ASTM develops standards for the materials themselves.
Hmm.
So an ASME code might refer to an ASTM standard for the specific requirements of, say, a certain grade of steel pipe.
Got it. ASME for the system design, ASTM for the material specs.
Broadly speaking, yes. And then for the oil and gas industry specifically, the American Petroleum Institute, or API, publishes really important standards like APR 5L for line pipe.
API for oil and gas. Okay. Is it mostly U.S.-based organizations or are there international ones too?
There are definitely equivalents and related bodies elsewhere. You have, for example, CWB standards used in Canada,
Yeah.
the EN standards, which are harmonized across Europe, GOSI standards historically used in Russia. It's a global field.
Any other areas covered by specific standards?
Sure. There are standards bodies focused on specific aspects, like the AWS, American Welding Society, for welding procedures and qualifications, which is obviously critical for joining pipes. There's AWA, American Waterworks Association, for drinking water systems. NFPA, National Fire Protection Association, sets standards for fire protection piping. MSS for valves and fittings manufacturers. It's a whole ecosystem of standards ensuring things work together safely.
It really paints a picture of just how layered and regulated this field is. It's not something you just jump into.
Not at all. It requires deep knowledge of these codes and a real commitment to safety and quality. It's a testament to how vital these systems are, really.
Absolutely. Now, folks, if you're finding this journey into the hidden world of piping as fascinating as I am, this is probably a good moment to remind you to hit that subscribe button.
Yeah, definitely do.
Don't miss out on more stories like this, more deep dives into the often overlooked things that shape our world right here on Tell Me More.
So yeah,
Yeah.
as you can hopefully see now, piping is, well, it's way more complex and way more critical than it might look on the surface.
Definitely. From the deep material science to the really intricate engineering calculations.
And even back to its, surprising history with things like hollowed out logs and redwood.
It really is a field that underpins so much of our modern infrastructure and industry.
Just think about it for a second. The fuel that gets gas to the pump for your car.
The clean water that comes out of your tap.
The energy generated at a power plant. The manufacturing processes that create countless products we use every day.
They all rely somewhere along the line on these unseen networks of pipes.
They really do. And what stands out to me is the constant evolution. The adaptability, the innovation in materials and analysis techniques, always pushing to handle new challenges, tougher conditions, greater efficiency.
It's impressive. This whole deep dive into piping, it makes me wonder, what other things that we take for granted, things that seem kind of mundane, what other seemingly ordinary parts of our lives have these incredibly rich, complex, maybe even surprising stories hidden just beneath the surface?
That is a great question. A really interesting thought to leave folks with. Maybe that's a thread worth pulling on in your own explorations.
Perhaps it is. Well, thank you so much for sharing all this insight today. It's been truly fascinating.
My pleasure. It's a topic I find endlessly interesting.
And thanks to all of you for joining us on Tell Me More Stories Told As podcast.